The concept of time travel has been a staple in science fiction for decades, providing an endless source of plot lines, philosophical debates, and ethical quandaries. But is it possible? But when it comes to the actual science behind the idea, there are numerous obstacles that make it largely theoretical at this stage. Let's explore the possibility of backward time travel. One of the major roadblocks in the path to backward time travel is the violation of the principle of causality. In classical physics, events occur in a cause and effect relationship, obeying a certain temporal order. Backward time travel would inherently disrupt this order, making it difficult to reconcile with our current understanding of physics. If you were to go back in time and alter a key event, the ripple effects could disrupt the entire fabric of space-time. Another obstacle is the law of conservation of energy. A trip back in time might result in an environment where energy isn't conserved, leading to potential imbalances that could destabilize systems or even contradict the fundamentals of thermodynamics. Paradoxes. The most well-known of these is the grandfather paradox, a thought experiment which questions what would happen if you traveled back in time and prevented one of your grandparents from meeting their future spouse, thereby preventing your own existence. Would you then be unable to travel back in time in the first place? This paradox presents a logical inconsistency that challenges our understanding of time and reality. Another paradox associated with backward time travel is the bootstrap paradox, which involves an object or piece of information that exists without ever being created. For instance, if you take a book back in time and give it to an author who then copies the text and publishes it as his own, where did the book originally come from? Some theories attempt to resolve these paradoxes. The Novikov self-consistency principle, for example, posits that the timeline is self-consistent, meaning that if time travel were possible, events would transpire in a way that paradoxes are avoided. Essentially, you couldn't change the past because any changes you made would already have been accounted for in the timeline. Another potential solution comes from quantum mechanics, specifically the many worlds interpretation. According to this theory, each decision or event spawns a new, separate universe. In the context of time travel, this would mean that traveling back in time would create a new timeline, avoiding paradoxes but at the cost of potentially getting stuck in a parallel universe. Even if we could somehow circumvent these theoretical issues, the technological challenges would be enormous. The construction of a time machine capable of such feats would likely require forms of energy and materials that are currently theoretical, not to mention the computational power needed to accurately target a specific point in time. Finally, even if backward time travel were proven possible, it would open up a Pandora's box of ethical and moral dilemmas. The potential for misuse is staggering, from altering historical events for personal or political gain to the unintended consequences of even the smallest changes to the past. What about forward time travel? Forward time travel doesn't present the same paradoxical or causality issues as backward time travel, and it's theoretically possible under the framework of Einstein's theory of special relativity. According to the theory, as an object approaches the speed of light, time for that object would slow down relative to a stationary observer. This phenomenon, known as time dilation, has been experimentally confirmed through the use of atomic clocks on fast-moving jets and satellites. General relativity further expands on this by introducing gravitational time dilation, where time flows differently depending on the gravitational field. For instance, time moves slower closer to a massive object and faster as one moves away. So, in theory, a person near a black hole would age more slowly compared to someone far away from it. While theoretically sound, the practical implementation of forward time travel is impeded by several technological limitations. First and foremost among these is the enormous amount of energy required to accelerate an object close to the speed of light. Currently, we don't possess the means to generate or harness such energy. To achieve near light speed, the energy requirements would be astronomical. Future advancements in energy generation, be it through fusion, antimatter, or even currently unknown methods, could provide the means to achieve the required speeds for forward time travel. Advances in energy storage technologies would also be crucial for any practical application. Assuming we could reach those speeds, the integrity of any material, let alone a human being, at near light speed is another concern. The stresses and conditions would be extreme, requiring materials that are likely beyond our current capabilities. At relativistic speeds, even a tiny particle could have catastrophic effects due to the immense kinetic energy it would carry. Cosmic radiation would also be a significant hazard for humans traveling at such speeds. Current technology does not offer materials capable of withstanding the immense stresses associated with near light speed travel. However, developments in nanotechnology and new forms of matter, like graphene or metamaterials, could provide the breakthroughs needed to build a vessel capable of such a journey. Artificial intelligence and quantum computing could play a role in simulating the different variables and conditions associated with forward time travel. High-level computations that are beyond human capability might be conducted by AI to model the best possible scenarios for time travel, including the ethical and societal implications. While classical theories like general and special relativity provide some support for the feasibility of forward time travel, quantum mechanics offers alternative perspectives that could lead to new breakthroughs. Quantum entanglement and the study of quantum states might yield insights into the fabric of space-time, and quantum computing could provide the computational power needed for such complex calculations. In the realm of astrophysics, the study of wormholes and cosmic strings offers tantalizing possibilities. A wormhole is a theoretical tunnel-like structure that connects two separate points in space-time. If a stable wormhole could be created or discovered, it might serve as a bridge for time travel to the future. Cosmic strings, on the other hand, are hypothetical one-dimensional defects in space-time that could, under certain conditions, facilitate forward time travel. Both concepts are purely theoretical at this point but could be areas of active research in the future. Forward time travel raises several ethical issues as well. If one could travel to the future, it opens up the potential for exploitation, such as bringing back advanced technologies or knowledge for personal gain. Additionally, what are the moral obligations for a time traveler who learns of future events, especially calamitous ones? The good news is that science is ever evolving. Research into quantum mechanics, parallel universes, and the fundamental nature of time itself may offer new perspectives. It's conceivable that breakthroughs in these areas could provide novel solutions to the challenges posed by time travel. While the scientific consensus remains skeptical about the feasibility of time travel, it remains an open question. The hurdles are immense, encompassing theoretical limitations, technological challenges, and ethical implications. Yet, as our scientific understanding and technological capabilities advance, the distant possibility of time travel continues to captivate our collective imagination. After all, science often turns yesterday's fiction into tomorrow's reality. Thanks for watching. Please remember to subscribe to our channel and give us a like.